This is the Amp Hour Podcast, released September 16th, 2018. Episode 407. Gregory, Charvat, and 3 new companies. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Gregory Charvat, author of Small and Short Range Radar Systems and the Chief Technology Officer at Humatics Corporation.
Back once again with a new title, but doing similar things, it sounds like.
That's right. Yeah, I wrote the book on what we're doing, so that helps. That helps in the job a little bit.
It does, you know, that recruiting effort is real easy when it's like, hey, we should just get the guy who wrote the book.
Yeah, well, that's why, Chris, that's why it's always awesome to write a book. I think you should write.
Yeah, I think you told me this before, but I still don't think I'm on board with this one. We'll keep talking about it.
Old media, man, old media. It's still around. It serves a purpose.
Dead trees can do things. Yes,
that's right. Well, dead trees last longer than software. We were talking about software earlier as we were trying to get the audio to work today.
Another day of audio woes, but yeah.
Yeah, and I'll tell you, like it's things are often a software problem, and I think it'll be a struggle in the future to maintain all of the wonderful media that we have today. The paper will outlive the digital, I believe.
That's true, and I have referenced this before, but I was at a talk with where Bunny Huang was giving a talk about tech, and he was comparing the frameworks of software versus a soldering iron, and it's soldering iron is a little bit more regular,
That's right. I mean, think of it. When they're digging up the landfills that are full of old televisions and CRT monitors 10,000 years from now, they're not going to find software down there. They're going to find circuit boards and lead and resistors and capacitors. That's what they'll find, Chris. Think of it that way.
Okay, that's good.
For better or worse.
So, Greg, for people who have not heard you on the show before, I will obviously link in all of the episodes you've been on before, but could you tell people a little bit about who you are and what you do?
Yeah, let's see. I started in the electronics hobby at an early age, like many of us did. In fact, back in the 80s, I started. I taking apart televisions and radios and things like that. In grad school, I taught myself how to make radar imaging devices and systems, and from that work, I was recruited into MIT's Lincoln Laboratory. I actually earned my PhD in applied electromagnetics. And at Lincoln, I built the MIT through-well radar, imaging radar, as well as created the project-based learning class build a radar system with coffee cans and wood. Yeah. And that thing now is going on 7 years continuously, and many universities, institutions, and so on and so forth have adopted it and actually improved it dramatically in some instances. So that's kind of cool. I was a visiting researcher at MIT Media Lab under Ramesh Raskar, where I created the time-of-flight microwave camera, so you could actually watch a pulse of microwave energy propagate across a target, let's say a book or a series of, spheres or whatever you'd like. It would be as if you could put on microwave goggles and see the radiation. So I did that. Wrote a book.
When was that? I don't know if I've ever seen that. I heard about that one.
I think that was after, sort of between podcasts.
Okay. Yeah, I was gonna say I just looked it up. The last time you were on here was 2014. Wow.
2014. We published that stuff, the microwave camera in Nature Scientific Reports in 2015. So it was.
Okay. There we go. Yep.
It was on the DL at the time, but that was another garage-based project. It basically Ramesh. I was a visiting researcher. I was basically kind of hanging out with all of his grad students and postdocs up at MIT once a month, and I would help them with their projects. And Ramesh says, I appreciate your help, but I want you to do something really creative and unique. What do you want to do? Think about what you want to do. And so I thought, I know what I want to do. It's simple. I want to see a pulse of microwave energy propagate across something, and I want to slow down the speed of light so I can watch it propagate.
Of course. All right.
Why not, right?
Yeah. Why not just change the nature of the universe?
So we did that, and I built this prototype and leveraging a bunch of the equipment in my lab here, and it worked beautifully. And you could actually, it was the coolest thing. You could take, like, let's say, here's a very canonical version of it. You could take a bunch of thumbtacks, stick them in styrofoam, which is transparent to to microwave radiation at our frequency of 10 gigahertz, and you could radiate it from different angles. If you radiate it from the side, you could actually watch the pulse hit the first group of thumbtacks, then hit the second group, and the third, and the fourth, and the fifth, and play
And
it back.
as you say, when you say watch, you mean you have a secondary observer, like another microwave receiver or something?
Yeah, yeah, you have a camera, you have a lens. So it was actually
Oh,
an optical system, but it was at the microwave frequency. So it was optical, and I had a single pixel, and I would scan it into one position, then I would ping the radar, then I'd
uh-huh.
scan again and ping the radar. So it was not a real time system, but it was all the same, and
Uh-huh.
the target was stationary, like taking a picture in 850. Everyone has to stay still.
Yeah.
in our
Okay.
in our case, you have to stay still for 45 minutes. Oh, we take the microwave picture. But unlike a still picture in the 1850s, 1840s, this camera would actually take a video of the microwaves traveling at the speed of light and slow it down. So that was the really super unique and unusual thing that we did. So you
Okay.
could it was you could watch the pulse, you could watch the flash of the camera travel towards the target, bounce off of stuff at the target, and back to the camera. You could see it, which was the coolest thing ever. You could actually see when the pulse, microwave energy scatters and bounces back and forth, just like light does. But
Sure.
with microwaves, we could slow it down so you can see it because vis-a-vis coherent processing, which is what I did for this thing.
I
You
don't
could
quite
act,
understand the filter. So you said there's a microwave filter for a camera? I don't understand the electromagnetic versus, I mean, I know that light is electromagnetics as well,
yes, it's all the
but
same.
like, but for in my mind, I keep those separate because they're both confusing in their own ways, you
Yes.
know?
Well, a lot of people do. What happened, if you look at Maxwell's equations and you start deriving them from scratch, which is a painful
On
thing to do.
Saturday night activity, of
Yeah,
course,
exactly.
you know?
At some point, the folks with the electromagnetics background, like myself, with the EM background, they go the fields and waves route, and the optics people make a few approximations. Now, us fields and waves people, we make different approximations to solve Maxwell's equations, but the optics people make a different series of approximations, and their approximations include um, the fact that their optical apparatus tend to have many, many wavelengths of, like their lenses are many wavelengths in diameter and width and height. Their apertures are like thousands of wavelengths. Their the distances between things are zillions of wavelengths apart. So they have this, like, they can make some approximations that we can't in the
Ah,
microwave world.
got it.
And so that's where the two fields part ways. And so, but what you can do is you can say, hey, I understand that fork in the road, that theoretical fork in the road. Let's go back to that fork and see what we could do with microwaves and optics. Let's just put them back together back at the fork in the road. Let's bring that fork. Let's make that. Let's get rid of that fork and see what we could do. And
You're like, you know what? Fork it.
fork it.
Yeah.
I think that's pretty funny. Yes, fork it. Fork it.
Yes,
Stick a
indeed.
fork in it.
Yes.
But anyway,
I'm
that's
done.
what you do.
Yeah.
That's what you
Okay.
do.
I still don't quite understand the logistics of that though. So like, what does a filter like that look like? Is it just a piece of material?
No, it's a measurement. It's a measure. It's
Oh,
just a measurement. So how do
so when
you
you spoke about a filter, I was, when you say camera and filter, I think of like a thing you stick in front of a lens.
right?
But you're saying like a mathematical filter.
I would say no. I would say method of measurement. I may have
Okay.
misspoke when I said filter. I think what I meant by that is we are a different wavelength. We're at 10 gigahertz as opposed to the nanometers at the uh, optical wavelength. So things look different, and we're only processing electromagnetic radiation at this longer wavelength. But it's all the same otherwise. I mean, the ways in which you deal with it, except it is physically the same, but the way by which you can process the data and acquire it is different. So it becomes a lot easier to do things like slow it down and watch it propagate across. To back up a little bit, it becomes easier to measure the time of flight. It becomes easier to see the radiation in some senses. You could do things like phase coherent processing, which are very difficult to do at the optical frequencies. You could do it at the microwave frequencies, and so using that, I was able to more easily measure the time of flight and actually do some stuff that is normally pretty hard to do. So anyway, that's kind of why it was cool. It was just sort of combining the two things, and it's fun to
Well,
combine stuff.
I think we're going to come back to time of flight here in a little bit.
Yes.
But before we get to your current stuff, you had another thing in the middle. Yeah, like I said, you've been busy. So you're currently the CTO of Humatics.
Yes.
What was before that?
Before that, I co-founded two companies with Jonathan Rothberg, and one of them is called Butterfly Network, which right now they are fielding a large number of pilot systems, I would call it, to key partners. It's actually an ultrasound on a chip.
Yeah, this is my friend who's a ER doctor told me about this separately.
Yep.
He's like, man, you got to see this new thing. It's like an ultrasound you could stick in your pocket for like $2,000.
Yes.
And he's like, I got to get my hands on one. And I'm like, oh, I think I know who helped make that. Like,
yes.
so holy crap, Greg! Like, what is this thing?
That was a cool project, man. That was awesome. That's
so tell us about it.
That's a tough one. That was awesome. So what we did was, we started the company. There's three of us: myself, another guy, Tyler Ralston, and Nevada Sanchez, with Jonathan Rothberg. Jonathan is a very successful serial entrepreneur, pretty wealthy guy now, and he likes taking on really nasty problems that wouldn't normally be funded by venture capital, like tough problems and things that will take sometimes years to figure out, and this was one of them. So we started the company as an ultrasound tomography company, and then we realized that the cost of goods for the ultrasound tomography didn't really align well with the market. So,
and tomography is like that's computerized tomography. Is
yes,
that right? Like a CT scan.
Yep, you could do it with ultrasound. You could actually transmit ultrasound signals through the body and do the same processing as you would with the CT scan. And actually, the ultrasound system gives you time of flight and phase information, which you can't do very easily
there it is again,
CT
folks.
Scan. Exactly.
Time of flight. Yeah, we're gonna have thematics here. Yeah.
This is a theme, and
yeah.
So you can do all that stuff with ultrasound. So we believe that the fact that you could do it with ultrasound allows you to make imagery that you couldn't with the CT, and also it's safer, and you're not blasting you with
less
X-rays
radiation,
and stuff.
right?
Yep. And as long as there's some FDA levels, and it's pretty easy to stable of those, and so it's a cool sensor. But we found out that the cost of goods for something like that is pretty high. And then at the time we were talking to this professor at Stanford University, Peter Jakob, who's essentially like the big proponent of what's called CMUT, which is a CMOS ultrasound transducer, which is, here's another buzzword for you, MEMS. Like the MEMS, IMU, and the MEMS is a buzzword.
Micro electrical mechanical systems.
That's right. Now MEMS is a buzzword.
That was bigger like in the 90s, wasn't it?
Yeah, kind of like, right around the time Smashing Pumpkins was really hitting it big, this MEMS sort of popped up around the same time.
Got it. Yeah.
But
they figured out they could make structures in silicon, basically.
It was pre-Britney Spears. This buzzword.
That's good. This all of our time-based measurements, our time of flight through time will be based on pop culture.
That's right. Now I kind of tune out of pop culture right around the Britney Spears time. I sort of tune out, but I don't know.
You missed some things.
What did I miss? What did we miss there?
Boy bands.
Really?
I missed a lot of it too, Greg, I gotta say.
Okay, good. I don't think you missed it necessarily.
Yeah, that's right.
It's kind of like work. Like I missed work the other day. I don't know if I did. Yeah. So getting back to that. So we built this prototype. The cost of goods was too high. The market didn't support it.
Got it. And this was like a huge, like an actual installed machine. That's the idea.
We built it. We built this thing. And it worked.
Okay.
This tomography machine. It was actually the world's fastest ultrasound tomography imager. Could image 2 frames per second real time, which was fast because there are other large tomography systems like ours. It was a prototype. It was racks and racks of stuff. But it would
I remember
scale.
your picture was for LinkedIn or something for a while. Was in front of racks of equipment.
That was the machine we built. Yeah. You got it. It had light bulb. It was big.
This is why it was confusing for me when I haven't caught up in a while. But my friend told me about this handheld thing. I'm like, I don't think Greg's working on a handheld thing. So
it wasn't. But what happens in these startups, as you know, they start out and they pivot. They do some pivoting, right? And that's pretty typical for all of them. And every startup I've been in has done their share of pivots, and some greater than others. But in this case, we started with that. We realized that it wasn't a good product market fit because the COGS was so high. So but at the time we were also talking to Pierre Jakob, and his thing is MEMS-based ultrasound transducers. So if you look at an ultrasound system, there are the probe that you see in the ultrasound cart. Uh, it's full of these piezoelectric transducers that are literally built with a high, like some guy or gal takes a tile, cuts these things up, and then
Yep.
hand solders electrodes to the end of them, and
Yeah,
like
it's like quartz, like
it's
high
quartz.
frequency.
Yeah, it's high
Yeah.
frequency
Okay.
quartz, and to get bandwidth, they put dampening on it, so they reduce the efficiency, and it's just
Uh-huh.
it's a beast, right? It's really great for
Yeah.
1960s technology, but it
Right,
is
but
expensive.
ultrasound is just like what, like 100 kilohertz sound wave,
No,
right?
no,
Or
the
higher?
medical imaging systems tend to be at like at the low end 2.5 megahertz, the high end 10 to
Oh, okay.
15. So
Oh, okay, okay,
they're
cool. That's
higher,
good.
high
I was
res,
gonna
and
ask about, okay, 2 to 15 megahertz. That's good. It's good to keep talking about frequencies with you, because you sometimes you jump into gigahertz, and I swear one day you're gonna be talking about terahertz.
yeah.
So
And I
I
also
guess we're
like to
talking about
talk
optics. So
about kilo megacycles. Let's not leave that out.
oh, okay. That's from your ham
Well,
stuff, huh?
actually, no. That's from my test equipment collection because the test equipment in my lab is all like pre
Got
1960
it.
stuff. So it's in kilo megacycle, so it can be
Mm,
confusing.
got
I
it.
might
Right. That's
switch to
your
that.
boat anchor collection,
Look
right?
at inches, mils, kilometers, millimeters, whatever. It's all the same, right? It's all the same.
That's right.
It's all the same.
Right.
So we're actually my book has mixed units of inches and meters and all that stuff. So
Oh man.
so
Yeah.
don't look too carefully, but it is a mixed unit publication. So there are. So anyway, this thing was a beast, but Pierre Kuryakov CMUTs sounded interesting, but they were still very much in the academic world. And so Jonathan made this decision, which was a good one, which was, you know what, we're not doing this tomography stuff anymore. We're going to make an ultrasound on a chip.
Yep.
And everyone's like, whoa, wait a minute. We kind of hired a team that was really well poised to make things with FPGAs and A to Ds and circuit
Right.
boards and a lot of
Big
people,
stuff.
big stuff,
Lots of power.
lots of
Yep.
power. We hired a bunch of people out of Chicago, actually, who were previously at Motorola. And we were going to do this thing, right? And all of a sudden, we're doing this thing on a chip. And Jonathan goes, I remember this. And I just was, I thought it was crazy at the time, but he says, Greg, don't worry about it. You'll figure it out. You'll figure it out. And I was like, really? But I was like, okay, I'm going with it. And he was right. We started to figure this thing out. And so we got Pierre on board
This thing being ultrasound
on
and
a chip.
also chip processing, right?
It
Okay.
was MEMS and chips, two things
Okay.
none of us had done before.
Cool.
None of
Yeah.
us.
Smart people doing smart things.
So
Great.
we figured out, like, so I took on the MEMS stuff. We had a smaller team at the time. I took on the MEMS stuff, and the other guy, Nevada Sanchez, took on the chip stuff, and then Tyler took on the imaging stuff, and then we needed circuit board to swallow the data and compute. So our colleagues from Motorola took on that stuff, and so we kind of divided it up. And my focus being on the MEM side, because I had a background in electromagnetics, flew out immediately, jumped on a plane to visit Pierre Kuryakov because we just signed him on as a scientific advisory board member. And I took our hardware team at the time and I said, all right, we're going to read every single paper on MEM, every single paper on CMUTs, the CMUT, the MEMS-based transducer. We're going to build a spreadsheet of dimensions and radio and frequencies and bandwidths, right? Because we have to understand how we're going to make this chip, how we're going to dimension the physical device. And then we did all that in 2 weeks, and then I flew out to visit Pierre. And at the time, I started to write this MATLAB script to compute the dimensions and then make it line up against the literature dimension. Because you want to know how much pressure you're getting, membrane thicknesses, heights, widths, all these dimensions of how you make this mechanical thing. It's really like a little electrostatic speaker, is what it is.
Yeah. Okay. Yep.
Imagine, a very, tens of microns diameter electrostatic speaker. That's all these things are. But it's hard to actually make in CMOS. So flew out to Pierre Kuryakov's lab. We ended up just working together with them on a few things, and that was that. And we started making these things, and
then at the end there was a chip.
right,
Huh?
right. And so we ended up making some chips that started to work, and then we had some initial success with extremely low yield, but we got one or two to work, and we ended up getting like small subsets of them to work, and then we ended up starting to get images out of them, and then we ended up raising some money against that. So it
Yeah.
was pretty.
Well, did you skip a step in here though, where you actually talked about like what the hell's on like how do you so like you as the guy who's figuring out some of the MM stuff and like but like does it look like is it a circuit diagram? Like what does it look like to go from this idea or is it kind of building on your peers work of like
I would
oh well they
say
already have
it
some
it
structures.
like not to get into too much detail, but I would say it started with reading his literature, getting a little bit of help here and there, and some advice. Then we made our own and started to gain confidence in it, and that was enough to get things started. And then what we did was we hired people who had done this before, you know, who had experience doing this at other institutions, other universities, and then we ended up, then it like just then it became our own version of it, which was different.
Right, right. I guess the question for me is like, okay, so obviously this researcher had not taken it to production, right? And you and your team were interested in taking it to
Yes,
production. So like, what was the different thing there? You know?
I think the different thing I think part of it is that's a great question. I think part of it is that people have tried to take this to production earlier, and a lot of their approaches for making the ultrasound chip tend to be rather old. So they ended up putting a lot of analog parts onto a chip that have a lot of phase variance, over fabric. You make a dozen of them and they're all different, right? So there's a lot. They're doing like late '90s ultrasound imaging approaches as opposed to modern day like digitize everything and use
Got
digital
it.
signal.
Okay.
So that was one aspect of it. The other aspect was I don't think it was as there. The fabrication processes available to us today are far more mature than they were 18 years ago when these
Right.
things. So
Right.
as
So, well, and
time,
I would imagine that too is like if you're at a lab, so like Case Western where I went, we had a semiconductor processing lab. It was what like half a micron or something like that,
right, right.
and they had grad students that they had at their disposal, and they were trying out a lot of things, and that's cheaper than going to a TSMC or a modern process. So I assume that having a little bit of money behind you allows you to tap into that network of expert advice.
I think it's all of those things. Quite honestly, it's
Yeah.
all of
Yeah.
that, but it's also there was a lot of special sauce that we came up with to make these things manufacturable because it's you start with the academic paper and not just peers papers but other people's papers, although he's the main person in this field right now. But you start there, but the academics make one thing and then they do their thing with that one thing and call it a success, and that's really their role, is to make that one thing and show
Right.
that
The
it's
output is the
possible.
paper, right?
Right, the output's paper. But when you need to make something with yield, then that's a whole different story. And so the way you know we were looking at it as a yield from a yield perspective, and we immediately one of the people we hired immediately an analog devices fellow who helped set up the
Yep.
MEMS
Yep.
fab in analog devices, because
Yep.
and that's the person who, she quite honestly, like, a lot of credit belongs to her for our early successes, because as electrical engineers we can dimension the thing and say we don't want this size and so on and so forth, but we don't know how to actually make it come out the fab and work, and she did. And so there's a lot of when you have the finances and you also have the experience, I think, that Jonathan brought to the table, which is he had experience making things on a chip that were kind of similar in a lot of ways to this, with like arrays of FETs and things, sensors, and for electrochemistry. That
And this
was,
is your this is the co-founder
yeah,
Jonathan.
yeah. He's really the he's the investor, founder, and sort of brainchild behind this stuff, and
Got it.
he's he brought a lot of experience to the table too, and he knew what resources to tap to make this a reality. He's like, let's do this. This looks a lot like some of the other stuff I've done before. I think we could
Yeah.
figure
Yeah.
out the rest. And he put us in touch with consultants and chip designer contractors that we used for the initial prototypes and things like that, that allowed us to really accelerate the program and
Yep.
allow it to be at a point where you can raise money against it and say, all right, this is doable. This does work, and we have a path forward here. And that's
Yeah.
what happened. And then I actually moved on to another one of his companies once we raised the money
Oh,
for
got it.
that
Okay.
one,
Got it.
and that's where Hyperfine came in. So we got to this point where the MEMS could image things, and then we got to the point where we had some serious progress on the chip itself, and everything was clicking. Now it's a tough problem. They spent years and years getting to the point where they are today, but that's where we're at a happy point. And then John said, I want to do. He came to me. He said, I want to do the same thing we did together with Butterfly. I want to start a new company, new lab from scratch, and we're going to do this other thing, and I want to do just that. So we had this party on his boat, and
Oh, well, okay, great.
Yeah.
Dr. Charvat here,
It was fun, and it was
the
funny.
esteemed Dr. Charvat is, giving tips on how to start chip companies out at sea. Okay.
Right, which is what we did. But it was interesting because it was actually a working session. So we had like IP meetings, we had tech meetings, and it was a lot of work. And then finally he said at 6 p.m., all right, guys, just stop working, everybody.
Cocktail hour, right?
Let's, relax, and I think we're okay. And then we kicked off the company, and that's hyper fine. Although I can't really speak at all about what they're doing. It's in stealth mode. I respect that, and the way he likes to roll out the companies is he likes to keep in stealth mode as long as possible. But that thing's going to be awesome when it does go public. It's going to have a similar impact, I think, to Butterfly for sure. But it's another really, and the theme that Jonathan's companies have, it's all medical, it's all hugely impactful. But then,
got it.
I was happy we started that company and built the first machine in 100 days. Then built the next one in I think 4 or 5 months, and then started hiring people that similar to Butterfly. You get people who are kind of generally good. Like I'm pretty broad, and then we get a couple other people who are pretty broad who can get something together working. And then as to make it better, you hire the key experts, right?
Yep.
Who are really good at it.
Yeah. Well, you have funding secured at that point, right? So you have a prototype which allows you to shop it around.
Yes.
And then you get funding, and then you can afford the super experts as well.
Yes.
And you can afford to have a team that's 100 people because 4 or 5 of them might be supporting the expert as a tech or an admin or whatever. So
yeah, that's precisely you kind of what you want to do with all these startups. I think what you do with these startups is you get. It's good to have people who are generally good at first, and then like yourself, Chris, and then who can kind of do a lot of different things. And then you get it to a point where you have funding, or it's clear you're going to get it, or so some nice point wherein it's worth. Then you get the experts. You have to pay for them. They're not cheap, but you get the experts in, and they make it.
You got to convince
better.
them too.
Yes.
I think that's the other thing. It's not just convincing them with money, but you got to convince them on vision too.
Yes.
And it's like,
yes,
someone who talks a big game is a lot different when they're holding a device in their hand. They're like, "Let me show you."
Right.
Especially when it's. And so I think the thing to call out here is that these are pretty high tech startups. I mean, this is not just like slapping something on a web server. This is this is some serious science.
Yeah.
This is great.
This is not that's. I think that quite honestly, as a good work with Jonathan, I learned a lot. He was a mentor in a lot of ways, and I feel like that's a good boot camp. So like, that's one advantage of working with a very people who are really aggressive like that is you're going to learn a lot fast and you can apply it to your next company, your next venture. But yeah, these are all hard problems.
You're gonna be feeling it at 1 a.m. when you're stressed out, but you're also gonna learn a lot, right?
Yeah, you will. And I think my recommendation for that is, you need to get into sort of exercise routine, whether it's a half-hour walk a day or something, to burn it off, because there's no point in stressing yourself out. There's always going to be some challenge. You get used to it. It's like you get acclimated.
The thing that I've been talking about recently with some friends is just like sticking, like understanding when to stick with it is kind of like the hard thing, but like people who are really good almost always stick with it, and they know when to bail, sure, right? But like you need to kind of wait through the pain at least.
I think the bailing thing is tough. I don't, every one of these, every company startup you get involved with is going to have some bad things go down. You know what I mean?
Sure.
There's always some tough times, and
that's the wading through it. I think you got to understand that there's some stuff there.
Yeah, exactly. There's always some crap that you have to work through because it's a pressure cooker. Everyone's under the gun, and the worst behavior, it will come out, and you have to acknowledge that you have some bad behavior yourself. You're bringing to the table, and
I don't, Greg. Sorry.
Oh, sorry. No. Yeah.
I'm perfect. Yeah. No, I'm definitely not human.
I'm sure people who work with me will, say the same thing. Like that's
Oh, we're getting to that. I met some of your coworkers yesterday.
Awesome. Oh boy. Yeah.
Oh boy.
It's interesting. I don't know. It's an interesting experience. I do think that some of it could be smoother than others. I think some teams work better together than others naturally. I think that there's like I do I do believe that there's a hiring strategy that I've learned over the years with these. I've been doing startup stuff now for 7 years, and I think I've actually learned. There's sort of an optimum way to hire too. You have to be careful. You got to watch out. You don't want to hire people with the big egos. That always causes chaos. You got to get.
Yep. Yep.
You just see people, team players who are willing to be aggressive. You want people who are not so analytical. You want people who just can take one data point, decide, and go. Because it actually costs more money in a startup to think about things and analyze them than it does to go. It typically
Oh,
costs
really?
more to
Interesting.
think about it and wait another week or whatever than it does to just go. Because you got to think about your burn rate. Your salaries, your burn rate, your fixed costs are just it's costing you X number of dollars per month per week, and
So you're just saying like because you're assuming the iterative approach and you're going to rework things. Is that kind of it? I
yes,
mean, you're not saying
yes,
like throw caution to the wind and just try anything. You're saying that
no.
once you have figured out that first path, try something, then bounce back and bounce, bounce, bounce. It's like a serpentine between ideas.
I think what you want to do is you pick the easiest one that's the highest probability of success, and you go and you rely on your experience to make the call and whatever data you happen to have at the moment, and just call the shot and just go because
Yeah.
you're not going to get better. I mean, sure, you make it 10% better information, but you'll spend a week doing that, and if you're burning $1 million a month, which is a pretty typical burn rate of a startup, uh, $250,000 for a week of consideration isn't
Right.
worth the money.
Right. Right. And
I
if the
mean,
prototype costs even $20,000, and you're
it's
doing some
cheaper.
active work on that. Yeah. Exactly. Yeah.
It's cheaper. Like it
Yeah.
really like
It's crazy.
it's what you want to see when you're running these teams and programs, which I've been doing. Like I ran teams and the programs with Jonathan. I ran the hardware team at Butterfly. I ran the hardware team at Hyperfine as well, and I do the same at Humatics. I run
Are you
hardware
forgetting the
teams.
names at this point? That you talk a pause there. I'm just saying, you've done enough
I'm
startups that it's
starting to forget the names exactly.
at least on these startups, these are actually like regular names. I mean, like, at least it's not like Cluesy.
Oh yeah, well, phone. We're not making phone apps here, man. That's
Yeah, right, right.
Oh, wait a minute. Now let's talk about this for a sec.
Oh yeah,
Technology.
we kind of got into this right before the show started, huh?
Listen. I think we have a problem in society right here, right now. Okay, and
A
I'm
quick
speaking
a quick break from the actual tech talk to talk about tech.
to talk. Let's talk about technology. Okay, so what amp our listeners, right? Hardware people, right? Aren't most of them hardware? Most of us are hardware people.
I think hardware interested at least. If they're, if you're listening to this and you're not at least interested in hardware, you're gonna have a bad time probably.
Yeah, yeah, exactly. Everyone here can pick up a soldering iron, and we know what a transistor is and all that stuff. Okay, so
Or well, no, we don't want to be exclusive there, but at least they're interested in doing so, right?
okay.
So.
So, okay, let's think about what technology is. I think the word technology, Chris, we need to take it back. Okay? It has
Okay.
been hijacked by the software and IT and phone app community. They've
Yeah.
hijacked it.
Oh,
They've
I know.
hijacked it. It's a
The
travesty.
easy way to see
They
this
don't
is
make
to.
anything. There's no circuit boards over there. There's no LEDs. Listen, when the archaeologists 10,000 years from now dig up the landfills and they look,
Back-
you know what
Back
they're
to the landfills. Man,
real
yeah.
landfills.
They're gonna find my trash.
they're not
They're gonna
gonna
find my
find-
shitty PCBs.
They're not going to find software down there.
They're gonna find my leaded whatever.
They're not going to
never.
find Facebook down there. They're going to find CRTs and circuit boards and things
I
full
don't.
of
I don't know
lead
if you're
stuff.
making.
That's a good thing, right?
I'm not sure that's a great point. I gotta say.
Well, I guess it's not a good. Well, look, it's not a good thing for drinking water. That's for sure. We could
Sure.
get that off the table. There's no question.
You're
about
just
it.
talking about substance and world changing type
It's
things.
a good thing for history, though, to find those leaded circuit boards that the technologists made, the real technologists, the people who make stuff, right?
I think you're talking about the substance of atoms versus bits, right? And I think unfortunately the thing. So like my example for when people talk about like, oh, I'm into tech, and I go, well, wait a second.
Oh,
Could you please define that? And they're like, well, I like getting new phones and I like apps, and it's like, oh, okay, that's just a different thing in my mind. And I think what you're saying too is like that's just a different word to them versus you.
I think that we need to take the word back. I don't think they should own that word anymore. I think it should just be the
Well,
exclusive
there's just
club of
more
people who make
people
real
there.
stuff.
Okay, well, maybe we just make our own word.
I
Greg.
think we need to make a word up for them
I don't think that's how it works.
because the word technology it kind of started actually at around the Civil War.
I did not know that.
It was actually it revolved around the ship the Monitor, and that was really the first time the word technology was used.
I mean, what if people like who are into like war history and guns were like, well, we want to take this word back. All these electro weenies are they're talking about resistors and soldering irons when we're talking about bullets and
Well, listen,
barrels.
if those people want to take it back, I don't think we can stop them, Chris.
I don't know, Greg.
Circuit boards aren't bulletproof. Like,
There's
not much we could do about it.
Are you working on any like Tony Stark-esque, weapon technology?
No,
here,
no. I used to do that stuff on Lincoln Lab, but not anymore. We worked on sensors back then.
Yeah, I was gonna say that's the seeing through the walls radar.
Yeah. And that thing, that's it worked beautifully. But yeah, that's how we work on these days.
Okay.
That's how we work. But it's good stuff. It's made for a reason, and there's honorable people doing stuff in the field, and that stuff's pretty cool. I think it's good to do a tour in defense because they are literally making quite honestly, they're making the cutting edge stuff because they sort of have a limited budget. Nation states have a limited budget. I mean, I'm not sure they're always intentionally unlimited, but I mean, the $1 trillion F-35 program is a pretty big budget. That's the largest defense program ever.
That's a big hot mess. Yeah.
A big program. I mean, geez, oh Pete, that's a lot. That's a lot of money.
Yeah. Yes, it is. Well, that's interesting because a lot of that stuff, a lot of the, I was walking around IMTS yesterday, so that's where all this stuff came from. And I was actually, I was there with the Bolt folks, and I was there with Mike Stitch from Hackaday, and John Bruner and a couple of the people that we saw, and but we were talking about like how the military and the defense industry kind of funds a lot of that like big tech, like you were talking about.
Yes.
And then as we were talking about that, Mike from Hackaday was saying like, "Hey, I just heard from Greg, and I think he's here." And I'm like, "No way, I'll give him a call." And so I called you, Greg, and I was like, "Hey, are you here at IMTS?" And you went, nope, but my coworkers are. And Humanics was there. And so I got to go see what you were working on. So maybe this is a good way to kind of segue into talking about what are you working on these days?
Sure.
This is public.
This is public.
That's helpful to talk about it.
Yeah, the thing is like, this one is this is really cool. So this is another very, very difficult problem that we've taken on too. It is tough, but we've nailed it. Now, basically, what happened was while I was working on Hyperfine and having fun with that company, people would reach out to me all the time with startup ideas and things like that. Especially after my book was published, and I reply to folks, and I reply to almost everyone who writes me, but this one professor from MIT wrote me. And he's an interesting guy because he wrote a book that I'm a big fan, which is this book called Digital Apollo, which is about the digital real-time flight control system in Apollo. The Apollo flew to the moon. The computer was flying. The computer was flying the stick and the thrusters the whole time. It was actually the world's first fly-by-wire aircraft was Apollo, which is kind of interesting to think about.
Yeah.
And it was funny because the first fly-by-wire aircraft was the hardest thing we've ever done in aviation. Like the hardest thing humanity has ever done.
At least it was aviation. At least it was low stakes, right?
Yeah, low stakes, exactly. Funny thing is, I'm actually going to meet. I might meet Al Warden this weekend, who was flying the command module on Apollo 15. So it's a funny aside.
Wow.
At a dinner party, we'll hang out with him. They talk shop. It'll be fun.
Boats, and astronaut dinner parties.
It's good. It's good time. So
Greg living the hard life. This is like Greg's commercial for. He's like, you know what? If you write a book, sometimes you get to hang out with astronauts.
You do. You do. I think you could write a really cool book. I think you could take what you've done with contextual electronics and turn into a book, and I think it would be awesome.
Maybe not. We'll see.
So,
anyways,
so basically, this guy, David Bedell, wrote me. He said, "Hey, I'm reading your book, and I wonder if I could do this thing." He goes, "I want to see if I can make a short range, super high precise GPS with microwaves. Can you what do you think about that? So I wrote him and I said, that should be a piece of cake. And
Oh
then
boy, that's
he's,
how. That's how. Okay, yeah.
everything's doable. It's just a matter of time and money. And this, we're not breaking the laws of physics here. No one's breaking the laws of physics. So I said, all right, piece of cake. Then he said, oh, well, can I come down and visit you? Let's talk about it. So I had him over on my sailboat, and we spent the afternoon on my boat talking
Okay.
about this.
Yep.
And so he told me this story about how he worked for Bob Ballard. Do you know who that is?
I don't know. It sounds
So
familiar though.
Bob Ballard is the person who discovered the Titanic shipwreck.
Oh, okay.
He is on TV all the time and on National Geographic and all that sort of thing. He's the most famous oceanographer in the world today.
Since Jacques Cousteau.
Yes, exactly. He literally, like Jacques, kind of took the reins of Jacques Cousteau. And he has his own exploration ship.
Nice.
You can actually watch it
What
live
about
on
Steve
YouTube.
Zissou? Don't forget Steve Zissou.
That's right, of course. So Bob, though, is an interesting guy. He's his thing, his theme at he's at Woods Hole Oceanographic Institute he was like, I want to make undersea remote controlled robots to do the nasty work, to do the mapping, to go really deep. Because at that time they had this submersible Alvin, which was a man.
Yeah, I remember Alvin. I remember that was in my books growing up. Yeah.
Alvin's still around, and actually they recently upgraded Alvin's the titanium sphere that you live in when you go down. You in
Yeah.
Alvin.
Yep.
And our chief roboticist, Pneumatics, designed and wrote all navigation software on Alvin when it was updated recently. So
Awesome. Yeah.
your life is in his hands. Whoever is diving on Alvin right now, and
Wow.
but it's anyway. So Bob,
I should mention too. I forget his name. I will definitely look at it. But one of the people who worked on some deep dive electronics stuff gave a talk at the supply frame meetup I used to do, and that is a fascinating field. Like stuff I just never thought about, like compressing capacitors. Like what happens when a capacitor goes down super deep and experiences tons of pressure? It's like, oh,
it blows up, it implodes, it just boom.
Yeah, I mean, like you have to have tons and tons of different considerations for high pressure situations like that I never thought of.
Yeah. There's a couple approaches. One is you put it in a pressure vessel, and in which case it can be at atmospheric pressure. Or the other thing is you could fill it with oil and let it be the same pressure as the outside as the water. And so the hard part is you need to examine and test the parts you use, because if there's a bubble in let's say a potted, like a chip or something, that chip will implode.
Yeah.
And take with it everything around it will get blown
That's right.
to pieces.
Yeah.
It's
right,
like a large, like an M80 going off on that circuit board, basically.
Right.
And so
it was Nick Bingham, by the way. That's who it was.
It sounds familiar because I've met a lot of the Woods Hole people because of these connections with this company. And
right. Yep. Okay.
And there's a really cool there's some really neat symposiums they have on robotics. The Center for Marine Robotics is a great conference to go to. In fact, that would be a really freaking cool thing for someone at Hackaday to cover, is to go to the Center for Marine Robotics conference every year.
Yeah.
Because the talks it's just like, you're like, wow. And I actually gave a talk there a couple years ago about short range radar, and there's interest there too, because it's hard to find these things when they recover them, especially when the weather's nasty or it's pitch black. Anyway, that's a whole different story. But it's a whole different. I mean, I honest to God, like if there's a break between stars for me, I'd love to just voluntarily go on a cruise at Woods Hole just to experience it, and it would be cool. But anyway, that place is amazing if you had a chance to see it. But yeah, Bob was there, found the Titanic, and on Navy money, I believe he like had some extra ship time left over and decided to take a look for the Titanic and found it. And that guy he's very aggressive wild man and super interesting person. And his theme his career is to use remote controlled robotics, not unlike how we use the Mars rovers today. We control them remotely. In the ocean, you could have more real time
asynchronous too, right? You have to because of transmit times and everything, right?
Yeah, but you don't have that problem with when they're in the ocean, because you could communicate with them, but the bandwidth connections are limited, and so there's pieces of full autonomy, pieces of semi-autonomy that you use depending on what your mission is or what phase of the mission you're in, And Bob just gets that. He understood that in 1984. And
Wow.
before anyone did. And there's a cool, the cover of National Geographic, I believe it's from 84, wherein there's this image of a robot 6,000 meters below the ocean surface with a cable going up to a control ship. The control ship has a satellite dish beaming signals to a geostationary satellite, beaming them back down to Woods Hole. And that was his vision, which he couldn't
Wow.
do in 1984. But he does it
Yeah.
today.
Yeah.
He actually implemented it today at the University of Rhode Island at his institute there. And it's called Nautilus Live. And you can actually Google that and watch their missions in real time. You actually get the same feed that Bob gets in his control room at URI, including the audio.
I was gonna say, is this laziness? He's like, I hate boats.
No, it's more like it's interesting. What he did was he took like the PhD level oceanographers and historians and all these people, and he got them off the boat. They don't need to be on the boat.
He's like, they are wimps.
Yes, they're wimps. Well, he's using them for their brains to think about what's going on, and then he may have some scientists on the boat, but usually not. But he has a super experienced crew that's laser focused on getting this equipment out into the water and back on, and so
fewer people puking over the edge, huh?
Oh yeah, that's exactly it. Fewer people puking, less money, less risk. Plus, you throw scientists out there for 3 months or 6 week cruise, they're not getting work done that they need to do. They're kind of hanging out. That's a good point. You know what I mean? So
yeah, right. So it's efficiency.
You just need them for when now the remote vehicle is getting on station. That's when you need them to tune in, right? And that's there's a lot to be gained. But when they're not tuned into that, they could be writing papers about what's going on. They could be doing other work. Like it is just an efficiency, and it benefits humanity to have that efficiency. And so what he's done there is that he's finally implemented that vision, and it's kind of cool to hang out in his control room at URI and watch what's going on. And actually, if you look at his YouTube feed, you get the exact same feed. Put it on your big screen at home and turn off the lights.
That's awesome.
It's the same as his control room. Okay,
see, now there's a Saturday night.
That is quite honestly, I actually leave it on in the background when I work because I find it interesting. And they actually dive on like World War II shipwrecks and all kinds of stuff.
Oh man, that is super cool.
It is really cool. Like you are seeing what everyone else is seeing for the first time. So
and that's called Nautilus Live.
Nautilus Live, yeah. Your listeners should check it out. It's beyond. It's actually really a cool thing. So Bob's involved in our company, but so Bob had here's one of the problems Bob ran into in working on his robots for the first time, his underwater robots, is that he couldn't navigate these things very easily. So when you're above the waves, you have GPS, right? And no problem navigation. But
just general triangulation type stuff. Yeah.
But when you're under the ocean, obviously, GPS signals, microwave signals, are not going to penetrate the ocean. So especially, they're not going to get more than a few millimeters into the water. Okay, now they actually need navigation when they're surveying a shipwreck, right? Sure. How do you navigate down there aside from using active sonar imaging and navigating off of the blobs on your sonar, which is what they would initially do?
I'd imagine if you could drop like a stationary point on the bottom of the ocean, if you could actually tether it, but there's not actually anything stationary in the ocean. That's the problem, right? No,
exactly. So what they did was Bob, working with the other founder of this company, David Mendel, created from scratch. They built from scratch using like Motorola DSP chips and stuff back then. This thing, it's an acoustic based navigation system where you drop by anchor a series of buoys, and then you've got a sounder on the host ship, and then you've got a special sounder on the ROV, on the vehicle, on the robot, and they all can ping, transmit, and receive. So they all ping against each other, and because they can all range to each other, they can solve the matrix of equations that give you absolute position of the ROV, of the robot or the vehicle that's being piloted, like Alvin.
So is the pinger the main ship that's sending out the base signal? Is that because that's also GPS?
That one is GPS.
Centered? Yeah.
And then the ones at the bottom are a local navigation network that are tethered to the bottom via anchors. And then the ones in the bottom make up a local network. They actually know the time of flight between each other. Then they ping to the ship. The ship knows its position vis-a-vis GPS.
Yeah.
And so now we know exactly where the network is undersea
Right.
relative to GPS, which is really good.
I mean, these absolute positioning problems it's just anything in free space, really, right? And
Right.
water really does bring you into free space because
Yes.
you have that third dimension.
Yes.
That's a very critical thing.
Exactly. And
Yeah.
so now you can navigate the vehicle. And so once you can navigate the vehicle, now it opens up a world of possibilities you couldn't do before. So what they did some really crazy things. So first thing they did was they started taking photo mosaics of shipwrecks. So
Oh,
you know
okay.
those
Right.
you've seen those photo
Yeah,
mosaics.
so like a photosphere that people have on their phone, that's from a center point where everybody goes and takes pictures around
Right.
them. Now you flip that script and you take pictures around the
Now
thing.
imagine it's 1994. You're going back to the Titanic, and you have your 35 millimeter camera, that pressure vessel, and
Yeah.
you use this high precision nav to trigger the shutter. Okay, and now you can get a perfect photo mosaic where they all overlap just right for the first
Yeah.
time ever. And now you get a
Yep.
really good picture of what's going on. So they did stuff
Right.
like
Because
that.
you could edge match before, but if you had like depth differences, you don't know where you are in free
You're in
space, then you
trouble.
don't know how to adjust the photo. Like everything's just kind of a guess, right?
Exactly. But now you can actually use the control system navigating the vehicle to keep perfect depth to within a centimeter. And then
Wow. Okay.
you can make sure that you trigger that shutter so that the overlap is, exactly a meter and a half on every single image, and then the mosaic just is perfect, right? It comes out perfect. And so that's one thing they did. The other thing they did, which was very interesting, it's more abstract, is that Bob was the one who discovered these high pressure, high temperature fissures. We have these tectonic plates that divide up
Yeah.
the surface of our planet, and the theory for a long time that on the boundary layers, at the edge where these tectonic plates meet in the ocean, there must be places where it's spewing super hot water and minerals and maybe even
Right.
lava and other
Like
stuff.
volcanoes, basically, or
Yeah.
like the San Andreas Fault, right? That's a
Yes.
big
There should
plate.
be a San Andreas faults, and on that fault under the ocean, there should be spots where there's these super hot springs. Okay.
Yeah.
But no one ever found these things, but Bob Ballard found them for the first time, and
Wow. Oh, wow.
he finds these things.
That'll get you on the cover of National Geographic. That's for sure.
Yes,
Damn sure.
like for the umpteenth time, he finds these things, right? And then what they found was astounding, which was the astounding thing that no one ever expected was that they were teeming with life.
Yeah.
Okay.
Yeah. The sulfur-based like crabs that are down there, like those transparent
Crabs,
and
worms, corals,
Yeah.
like fish, like all
Life,
kinds of fauna, you name it, it's there.
finds a way. Yeah.
It found a way. But the funny thing is, normally at the bottom of the ocean, there's not a lot of life, much at all. But at the fissure, there's tons of it, right? A huge amount,
right.
shocking amount.
It's the reverse oasis, right?
It is, yes. It's pitch black. There's no photosynthesis happening, no nothing. And so that was shocking. And so what else is happening around these fissures? So what they did was they instrumented an ROV with this pinging system, this high precision nav, and they used to do something very unique. There's this plume of like black, what looks like smoke. It's not smoke. It's like full of rare earth metals and chemicals and all kinds of weird stuff. And what they want to do is find out, like, what is in that plume? What does a plume look like in 3D space? What is the shape of that plume? Where does the plume fall? How does it interact with ocean currents? So what they did was they took the ROV with the high precision location, and they made a 3D map by raster scanning it like an old dot matrix printer. Raster scan it, next page, which raster scan, and imagine you raster scan a page, and the next page is the next depth. You go up to like 10 meters higher down, do it again, and 10 meters up higher, do it.
And that is a thankless job right there.
Right, and no humans wants to steer that manually in ROV, which is what you'd have to do before this technology was available.
Well, the other thing I think about
So that's
is
what they did.
like I said, the ocean currents are just moving you. I mean, like that is just that is a constant thing. You are always moving because of the flow of the water.
Right. So you want a map of this thing. So they actually use this technology to make a 3D image and a map. And in that map, each pixel, each voxel in the 3D image was the chemical composition. So each voxel was like, at this voxel, this is what was here chemically, and by how much and what quantity. So you had this multifaceted voxel map of what was coming out of those things, which was staggering to see in the 90s, right? So that was one of the things they did with this tech. So David's on my boat. He's explaining all this crazy stuff to me. And meanwhile, I'm a really terrible listener, so I start daydreaming about how we could build this thing, right? And I'm like, yeah, I'm convinced.
Engineers always go straight to the
All
implementation.
right,
You
I'm
know?
like, okay, blah blah blah. All right, this is cool. Okay, so then we start. I tell him, I think I'm totally confident we could do this. And we talk about. No, we don't
Oh
get into
man,
too
have I?
details.
I don't know if I've ever said it on the show,
Yeah.
but whenever an engineer, and I'm an engineer, right?
Right, right.
But whenever another engineer says, "Oh, that's easy," my ears always perk up because it's like that's like a downsampling of total considerations.
Mm-hmm,
And I told this to my girlfriend,
mm-hmm.
and she said, you said that to me the other day, and and I'm like, oh yeah, so it's just like an engineer thing. Okay,
Well, I think
so
easy to us means
easy,
it's
easy to
feasible.
think about.
It's
It's feasible. That's the real word, and that we say easy, but it means that I can at least think through the steps.
It may mean
right?
we need to spend $60 million in 4 years.
Exactly. Yeah.
But
right.
it means it's tangible. It's feasible. We
Yes.
should be able to do
Yes.
this. And
I can think of a way to possibly do it.
yeah.
So, anyways,
and so
you did
we
that.
did that. And but I mean, David understands this. And so we did that, came up with an idea for the company and a technology pipeline. And so he took that back, and then he found a business attorney guy, because you need a business person, because as engineers and technology people, we should be honest with ourselves, what we're good at and what we're not good at. And you always need a very good business person to help you set the company up, to help you
Yeah.
find
The
the
legal
market,
piece.
do the
Yep,
legal
I
piece.
agree.
There's a lot there.
Yep.
So we found that
Yeah.
person, and that's the person that will raise the money as well and do very, very high value stuff. And that's a lot of legwork. So we found this other guy, Gary Cohen, who's great, who's been raising all the money for us and keeping all that, the ship on the right course, and helping us get to the market, the right market for our stuff as well. So we found that, we got this, and then so that was really our initial. And then there's another fellow at Woods Hole, this guy James Kinsey, who wrote the software to navigate Alvin and many other things. We got him because, like, I'm a sensors person, but I'm not going to understand how the heck this thing's going to hook up to a robot. That is equally as difficult. And so we got him. So there's the four of us, and kicked off this company together. And initially, the plan was there's this Time Domain Corporation, which basically pioneered what's known as ultra wideband. They've been around for over 20 years. They were for sale, and our initial plan was, let's raise some capital to buy them. We will, with our backgrounds in robotics and our backgrounds in radar, we will find, and our Rolodexes, which, with David Mendel and his background, everyone loves him. He's a wonderful man. He has this wonderful golden Rolodex, being at MIT all these years.
Yeah, that does help.
It is a
That sure don't hurt with
big help. We will find.
I mean,
this
finding some
application.
normals on that list might be kind of weird, but like
We're gonna
it's
take
like, can't find a plumber, but if you need someone to do high speed radar type
exactly.
stuff, yeah, I got a guy.
Let's talk to. Let's call up Bob. Let's see what he thinks. Bob Ballard and all
Yeah.
these people and these astronauts, all this stuff. So we're like, all right, we're gonna buy these guys, and they'll be part of our team. And they've got some awesome technology, and together we're going to find the markets, and we're going to incrementally prove it. It can be approved. And we spent some time. We flew down there. David's plane. He's a private pilot, to talk to them, and so we made an offer. Another company was also offering, and we lost the bid to buy them. And we stepped up and lost the bid.
Oh,
and
man.
so we're like, uh-oh.
So you also showed your hand, yeah, okay.
Uh-oh. So it's like those 80s movies where the record stops. It's like, whoop. Now what do we do? So then everyone looks to me and says, well, Greg, this is December 2015, right after, like a month after joining the company. Greg, can you make something that's better than their stuff? Can you make something? We have to make something from scratch.
So I went back out on a boat and thought about it. Yeah.
So I'm like, all right, fine, I'll make something. So I go back to my lab, and I spend like 4 months, and then we build our first prototype, and we demo it at this thing called Amazon at Mars, which was a machine and robotics symposium that Jeff Bezos sponsored out of his own pocket, and he puts on an every year Palm Springs, and this was the very first Mars conference. Jeff asked David if we would demo our product at Mars.
Jeff
Jeff Bezos.
Bezos
Yeah.
asked your co-founder if you could demo your
Yeah.
prototype at a brand new conference.
Yes,
for
which we
robots
didn't
and
have,
machines.
by the way.
Is this after they bought Kiva? Is that why they did the Mars?
Yeah,
thing?
yeah, because the
Is that why?
Kiva people were telling
Yeah.
Bezos and his people about us and our vision,
Okay.
which was to
I was wondering about
locate
that.
robots.
So like Kiva Robotics, if people don't remember, Kiva Robotics was the it's like the really low squat robots that basically pick up shelves and then move them towards people. So like Amazon bought them because obviously they do tons of warehouse.
Yeah,
type
yeah,
stuff.
exactly.
And this will become relevant, I'm guessing, to the conversation.
Yeah, so those guys were excited. A lot of people are excited about Humax because our vision is to locate robots, just like David and Bob did under the ocean. And so they're like, can we demo your thing? And this is right when we lost the bid to buy Time Domain. And we're like, yeah, sure. So I go back to my lab in Connecticut and make the thing from scratch. That we're going to demo.
Yeah.
And then we get it working. And we
Let me just pause and say you have been busy, Greg.
yeah, we've been kind of busy. Yeah, it's hey, look, no risk, no reward, no pain, no gain. Yeah, it was crazy. So we built this thing, right? And like, it was really brutal. And we get it done. My second daughter was born during this time while we're building this thing.
I was also going to say, yeah, you've been having a couple kids
Yes.
too, and like, not.
I've got a wonderful wife, and she's very supportive of the entrepreneurship. Her criteria is that she wants to stay in our nice little town of Guilford, Connecticut, and so that's what I do. I stay here as home base, but otherwise she go crazy and do it. So, a spouse, you mentioned you have a new significant other, Chris. This is something that you have to find that under mutual understanding that they have to accept the piles of old oscilloscopes and junk for one thing, which comes with all electrical engineers. Obviously, Dave Jones, his wife, is very accepting.
Yep.
Mine is too. I have lots of piles of junk, and I'm sure yours must be, or she must be getting acclimated to it at a minimum. This is a key thing. All listeners must go through this, I would think. Those of us who are married or inevitably will be. It is a thing. Anyway,
it's an important partnership. How about that? It's probably it is your most important partnership, maybe followed second by your co-founder type thing, right?
Yeah.
And often that startups are talked about like marriages. So finding good people to work with.
They are. But here's the thing with when you have piles of junk, just as a side, when you buy some big piece of junk on eBay, you can always you got to line up the shipment of that when your wife's not here. That's part of it. You don't want her to see all the junk coming in. Just a small sample of it. Like if she only sees 1 in 5 old oscilloscopes or radios or whatever the hell it is come in, that's okay. But don't let her see other ones coming in. So especially if a delivery truck shows up and there's a pallet of crap, that's the one you don't want her to see. Anyway, just piece of advice.
That's the spot.
I think all the married folks here, men and women both, will agree that's probably good advice.
Right. It is our curse to have more stuff. My curse is I was just moving, but as a quick anecdote, because I really want to hear about what's going on here. One of the guys at the meetup that we just had the other night, he was telling me he used to work at a company that did amplifiers for that sold to ham radio.
Oh yeah.
That sold for $10,000.
Oh my god.
And he said the guys would show up with piles of $10,000 in cash because they'd be scrolling away money over the years, and they didn't want their significant others to know about it.
Of course, 10,000 is a lot of cash. That's a big money right there.
Yeah, that's quite the that's quite the
ham guys
the
will. Some of them will. Ham guys and gals will throw the money down on stuff. I'm a little more frugal as a ham. I like to make my stuff from scratch because I just like the experience of making it.
Yeah, and you get in there, you understand how it works and everything. Okay, so speaking of piles of money, Jeff Bezos.
So Jeff's like, I watched these guys at the conference, blah, blah. So we don't have a prototype. So I go back to my garage at Guilford. I build it over the next 4 months. I build the hardware. I get to work in MATLAB. And then James Kinsey from Woods Hole was helping us moonlighting. And he comes in and develops the nav software for this thing. And we have it done by mid-March. We ship it out there, and Bezos pulls out the red carpet, paid for all the shipping for everything, it was like
That's the red
unbelievable.
carpet, huh? You hang out on boats with astronauts, and the red carpet is
They
Jeff Bezos
shifted.
giving you his UPS number.
Yes, exactly. No, no, he's actually sent a courier service to get everything. And
This is still a low bar to jump over for the world's
well,
richest man.
there's
I'm
more.
just saying, Greg, you're letting him off
I
easy.
am. Well, he also
I'm sure Jeff is a,
he had open
anyways.
bar everywhere, which was really nice too.
Got it. Okay. All right.
And so then there's a talk we had to give, right? So David Bindell gave the talk, and he's an MIT professor, so he's like good at this. He's damn good at these talks. So he gives the talk, and we do a live demo of the machine, and we demo it, and it works. And actually, like the theme of the conference was Jeff wanted every single demo. He wanted a talk and a demo of something, and our demo was the only one that worked.
Hey, all right. That's a good sign.
Yeah, so that was kind of nice. And
ways to stand out.
we stood out. We worked, and we had the only question that he asked, at least in our session, was how does it work? And of course, that's the one thing we can't necessarily answer in detail. But
Well, I think you do have to say a little bit here, at least what it is, because you don't have to tell us how it works.
of course not. But we'll talk about what
I
it
think
is.
radar.
It's a high
So
precision.
what is it?
It's not
Because
a radar. It's actually
I'm just saying, with you, Greg, it's always something.
it's always something.
Millimeters or
So if it's a short range, high precision GPS is what it is.
Okay,
We've
that's a
got
good way to say it,
GPS
yeah.
on our phone, and it's
Yep, yep.
invaluable now, the 21st century. Now,
Now I get to see both of these at IMTS. You guys
there's
were
two of them.
your team.
Two flavors.
Yep.
Yes.
I have to say your wording on it is very confusing because the one you just released was the centimeter based system.
Yep.
And then you also have a millimeter based system, but that refers to the accuracy, correct? Not the wave, not the wavelength.
Exactly. Yes, that's the
Yeah.
precision actually.
That naming is very bad.
I know. We have to figure out. We're doing our
Right.
best, but
Because you always talk about millimeter wave stuff, right? I mean, like that's your thing,
that's
and it
part of what I
probably
do.
isn't. Yeah, well, I mean, just like the waveforms that the wavelengths that you're using are probably in those ranges, and so
I
yeah,
think our
anyways.
point is that like it doesn't matter what wavelength you're at for what we're doing, but
Got it. Okay.
it's all about the precision of the instrument, right? And
Got
so
it. Okay.
what we've developed is something that it's local. It's short range, out to 500 meters, 0 to 500
Yep.
meters,
This is the centimeter system, the centimeter accurate
Yep.
system, correct?
and
Okay.
it gives you 2 centimeters or better precision, which with that kind of precision is more than enough, is good enough, actually more than enough, to navigate autonomous robots all over the factory.
Which is why the Kiva folks would be very interested in it.
Exactly.
If I could paint a word picture, there was four units that were kind of like lofted and up above at various random positions, and then there was a little robot on the floor that had a predefined path. It was kind of like going in a figure eight. It also had two things, two of the receivers on it, receivers / transmitters, because I think it's both.
Yes, they are. Yeah.
And then there was a third transceiver that was just handheld, so you could also see them. So then it was all visualized in 3D space on a laptop,
Mhm.
so you could actually show where they are in space, but it was very accurate.
Yes.
So kudos on that.
It is. It is. Why is this important? Why do you need short range, high precision GPS? Well, it's in the factory automation world. It is the thing that's missing. Okay, it is
Sure. Yeah, I mean, like you think about getting a GPS signal even inside with your phone is kind of tough sometimes,
Right.
and then that's from satellite based. You're now basically making the satellites and then also making the receivers.
Exactly. And not only that, we are substantially more accurate than GPS. And so
That's true.
you
Yeah.
need that accuracy, because when you're talking about things at these shorter ranges, 100 meters, 10 feet even, in the case of our booth at IMTS, the precision needs to be really good to navigate a robot that accurately and that precisely. So
Right.
GPS couldn't do that. And so what we have is something short range, but really accurate. And
Right.
it allows for robots to go to navigate around the factory, and that is missing today. It doesn't exist today,
Right.
and that's what we're.
Well,
that's what we bring. To
we
the
should
table.
also talk about the other systems that are there, because I think Joshua was talking to there, and Josh and Chris are two of the people I talked to there. They mentioned optics, or optical is like using machine vision is a very common remedy to this same problem.
Mhm.
But then there's shelves in the way or stuff in the way, right?
Machine vision works, but what happens is it records the area and uses what's called SLAM, which I forget what the acronym stands for. Basically, it remembers what things look like, but if something changes, it gets all screwed up. And in a factory, there's a difference between an academic project or a hobbyist project guiding a robot with a camera and a factory. The requirement of a factory that's making stuff to modern standards is every operation, every time that robot moves from A to B or enables some other process to happen, like put a screw or nut or bolt here, or pick up and put it there, the decision needs to be right 99.99% of the time. That is to say, the robot can't be off by more than 2 centimeters. It can only be off by more than 2 centimeters 1 in 10,000 times it does that operation.
Yeah.
And so,
and even then, we prefer that not to happen.
Yes, too. Exactly. Even then, you should be better than that. And so that's why machine learning is terrible at guiding robots, because if the machine learning stuff can't guide robots to that level of repeatability and accuracy, but it can. What is really accurate is GPS. When I drive to Boston, right. It's always accurate. It tells you right. It's right more than every time I've driven to Boston. It's right. Okay, it's not right like with machine learning.
It's not quite 2 centimeters.
It's not right to 50% of the time, like machine learning, or even 80% of the time, which is aspirational in the machine learning world. It's right all the time. Now,
wow, okay.
Machine learning starts to work really well, not for navigation, but when you have a super controlled field of view where you're looking at, let's say, a printed circuit board and you're aligning a part or something like that, where it's trained to look at something that's always the same. That's where it does.
And always like the same angle as well,
yes,
like straight
yes.
on, dead on, not angled at all, not recalculating.
Yes, but when there's people walking around, when there's inventory moving around, and the map doesn't look the same, it gets befuddled. Okay, and that's why you need navigation. So
there's other systems out there too, though, right? So there's also LiDAR that is on the device, right?
LiDAR is not navigation, though. LiDAR
is
to look for obstacle avoidance. Now, you could make a SLAM map just as you would with machine learning and vision with LiDAR data, but it has the same problem where that shelf of parts moves over here, then it gets all screwed up. So it may be able to, it learns and adapts, but it's not at 4 nines, okay? And so to get to 4 nines, which is the requirement in the industry, it needs to be very, very repeatable and accurate. Now, what is radio navigation, GPS, LoRaN, and indoor GPS hits 4 nines, and that's why this is so valuable.
Yeah.
Everything else.
Well, what about other
systems
though? Like we've had the Valve folks on a bunch with their Lighthouse, that kind of thing.
Valve, so what about
Lighthouse, that as well?
Lighthouse. I don't see people using Lighthouses to assemble automobiles at the Ford Motor Company assembly.
Sure. No, I'm just saying that as a comparison technology though.
They're not at 4 nines.
Laser scan.
That's fine.
So that's the same thing.
They're not at 4 nines. They're not there. They're not going to get there anytime soon. But they're in the consumer space, which we've looked at before. The requirements in those consumer spaces are pretty light. Manufacturing requirements are very, very stringent. Like what we're shooting for Humatics is
well, I think the price points kind of play that out too, right? I mean, manufacturing is willing to pay high premiums, right? Exactly.
Yes.
And so consumer
space. But certain technologies don't scale to that accuracy. They just don't. And I think that is one example of one that doesn't.
Hearing the 2 centimeter accuracy with the 500 meter range that's what's
you're not getting that with Valve. Lighthouse will not get you that.
Right. I mean, just any kind of light based technology, you start to have interference. You have beamform problems, right?
Light based technology tends to have a very narrow field of view, and for accuracy numbers we're looking at, it doesn't go very far either. So it's you're talking meters as opposed to 100 meters. It's just not the same. I mean, it is a sensor competing against it necessarily. What you need is a plurality of sensors, but ours is the one that's missing right now. If you want, like we demonstrated at Eckhart 2 weeks ago, if you want a robotic pallet to drive itself out to the loading dock and have material put on it and drop to the assembly line, and then have its material being lifted off and stuck onto a car, you're going to need our stuff to do that. You're not
so what are they doing today? What is the state of the art today? That's kind of the important thing.
There's humans in the loop. So what happens today is you have assembly lines that are on it's not necessarily a conveyor belt, but a chain. Like if you've seen Auto Factory, they're instrumented, they're precise. The assembly line precise. The robot is bolted onto or near to the assembly line precisely, and the robot is precisely pinned to the assembly line, so it has precision relative to the assembly line. But then to give the robot pieces and parts, humans are involved in getting the material from the trucks to the robots. And then there are other operations that are so complicated because humans have to use their own eyes to locate stuff that humans put the parts on the cars. And that's just an example. But what we
Got
would
it.
enable is
Okay. Well, what about like a Kiva as well? They have lanes, right? So they have like a XY grid that the robots go onto,
yes.
but then they just kind of tell where they are in free space and make sure the carts don't run into each other. And they, if there's humans, they also say, no, there's a human in the
Yeah, they
lane.
have lidars and
There's
they
not supposed to
stop
be
it
human.
and stuff. And
Yeah.
there's a lot to that. The Kiva stuff uses very conventional stuff, and I can't really say too much about it, but I think it's very conventional and
Yeah, no, I'm going off videos that I've seen, really. And so I
Like-
don't think that's
like
nothing
what you've
secret
seen.
there.
Yeah, what you've seen of Kiva is on the videos is exactly right. You see how the robots navigate. You see them, it works. It could be a lot better. And our stuff, because we're shooting for 4.9s, our stuff could be potentially a big enabler for them as well. And so it's
Sure.
it's enabler for anyone who wants to use UGVs on manned ground vehicles, or wants to use them better. So it's a key thing, and that is the centimeter scale stuff. And then there's another thread of our technology, which is the next thing in the pipeline. Right now, we sell the centimeter scale stuff as of Monday. We're selling it, and the next level up is the millimeter scale stuff, which is to say, when the robot pulls up to your assembly line or your workstation, when the unmanned ground vehicle drives up there with a load of parts, it only knows where it is within a couple of centimeters now. That's not good enough for an assembly robot to pick up something and stick it on a vehicle yet. It's still not that good.
Right.
So that's why we developed the millimeter scale, what's called the K1000. So that's a shorter range system that goes out to nominally 10 meters. And what it allows you to do is when you're close, it gives you millimeters to 4.9s, to 99.99%. So now you know to within a millimeter where your cart is. That's enough to pick up something and stick it on a car.
Right.
And
exactly.
so that's another that's the other piece that's missing, and that's why we developed both threads. Is that we want to actually enable, like, you remember the movie Star Wars where you see the robot assembly line there, it's a fully automated factory and they build the robots. Well,
dude, you're not talking about the prequels, are you? Are you seriously talking about the prequels?
Yeah,
on the
yeah.
show?
Well,
Oh
someone
my
has
god!
to see them. I'm not a fan.
Oh boy!
What?
This interview's over.
Oh, come on. Have you seen them before? They're great. I mean, that's literally Jar Jar's my favorite character.
You just lost the entire audience, boy.
Well, you guys didn't like. You didn't like
hanging
that
out
guy?
on boats too much.
I thought that guy brought a chill to the thing, and I really like the fact that they threw romance into the story. You didn't like that?
Okay. All right. We're done.
Oh, that was like the best part.
Oh boy.
No, just as an example. Okay,
yeah,
that's an example of a fully automated factory.
I
but
think
science
what
fiction.
you're talking about robots in general, and I think that's good.
Like
and
it adds like a level of automation that doesn't exist today, and that's what we enable TMAX. That's what our focus is, and that's why you see both threads. So you've got the centimeter scale can get the material there, or it can navigate all of the robots to centimeters to do whatever they have to, and material handling is one example. And then the millimeter stuff allows you to instrument things, fixture things. We call it virtual fixturing. Now, that cart that's on wheels, it may as well be bolted to the ground, and we measured it with a LiDAR because we know where it is to less than a millimeter. Now we could do machine operations to pick up stuff and mount things. So that's the theme of Humatics, and that is our focus, and that's what we're enabling.
Nice. Yeah, I like that virtual fixturing thing. And I mean, that played well at IMTS as well. I was walking around with a friend early on in the day who had not done a lot of machining stuff. And he was kind of like asking me, he's like, well, what is the hard part about machining? And not that I'm an expert in this, even in the slightest. But I said, one of the things that I always struggle with, and it seems like a lot of the things that people, when they're doing machining, deal with, is like, what is the absolute reference, right? Where is 000 axis coordinates, right?
It's a tough problem.
It is a tough problem. And that's what, so like you think about, okay, so you put something into a vise, is the vise 000? Or is is there some arbitrary point? And if there is some arbitrary point that's 000, where is the vise in relation to it? And then where is your piece of material in free space in relation to the vise? And then how do you do all this math backwards? And then how do you do the reverse kinematics for the robot arm that's in there, or the milling head, or whatever? And like, that is a lot of machining and just robotics in general, is where is stuff in free space? So if you guys are solving that, then that's a good thing.
Here's another way to look at it. I think you consider the coordinate frame of a machine tool. we with the millimeter scale stuff, the K1000 stuff, we project that out onto the factory floor, 10 meters radius. That's what we do. We project it out in 3D free space out to 10
And
meters.
why
That's what
would you
that tech
why
does.
would you project it out though? You're saying that like, you are giving a new 000, and then
What
everything
we're
adjusts to
saying
that.
is take your 000 off your machine tool, and now we can navigate relative to that to a millimeter out 10 meters away.
So, okay, so I'm guessing. So, let me explain the demo as I saw it yesterday. Maybe that'll help too. So, the demo yesterday was there was a. So you have your four coordinate system GPS thingy up in the sky, and
Yep.
then there was a small device that had a little antenna looking thing on it, and then on top of the antenna looking thing, there was a ping pong ball, and then the robot. You could move this fixture around. The antenna looking thing was movable. You could move that within a certain area, and then the robot always went and picked up the ping pong ball. That
That's
was the
right.
demo that I saw because it
Yep.
did, yeah. And
And it put it in
so
a box for you.
and I put it in a box, right? The box was fixed, uh, and so you're saying though that this is relevant in the machining or the factory context because you might actually want to move that thing around in free
Yes.
space because it might have just come into the frame as from another robot, right?
Well, imagine that thing that holds the ping pong ball. This is where you're a little abstract. Imagine where we're slightly abstract here. So imagine that the thing with the ping pong ball is stuck to a parts rack, and you're from the Midwest, so you know what the parts racks look like that go in and out of auto companies, right?
Yeah, that's the only way you actually know what a parts rack is if
If
you're
you're
from the
from
Midwest.
Ohio or Michigan or Indiana or
Yeah,
Illinois, you know
yep,
what that
right,
looks like.
right.
So they have these parts racks. They're usually made of steel, and they'll load them with like hoods, windshield wipers, alternators, whatever, and they're all like positioned accurately inside the parts rack. So imagine you have the millimeter scale beacon, we call it, on the parts rack, and the parts rack gets delivered by an employee, a factory worker, or is driven there automatically by unmanned ground vehicle and dropped off somewhere arbitrarily, but within the assembly robot's line of reach. Okay, and now the Humatic system pings the parts rack to within less than a millimeter and tells the robot, here's exactly where that parts rack is. And we know what kind of parts rack it is. And the robot says, okay, great. Now I can start picking up alternators and bringing them over here and sticking them on the car. I could pick up
Right, yeah.
hoods and
Right,
drop
stuff
them
that our
off.
eyeballs do right now, right? I mean, that's so if the robot is now a human, it says, "Oh, look, a cart," and then I know how to,
I know how to pick up
move
the
my
parts.
actuator, which is my hand, to
Yep.
pick up a part, right?
And that's why that demo is so powerful, because here we have a small ping pong ball, and we have our beacon, and you can stick the beacon anywhere, and the robot picks it up every single time and puts it in the bin at the same location too, by the way, every single time. So that is symbolic of all the things we can potentially do with the technology, from automatic assembly of things that are now highly manual to we enable that to even packing boxes automatically. That's why it picked up a ping pong ball, it dropped it in a box.
Right, I think that's a good point too, because obviously at the show there was tons of robots, including the pick and pack robots that are out there. But the pick and pack robots start within a very significantly constrained frame, right? I mean, they have basically there's a camera, and whatever the camera sees, then it knows, okay, there's an object here. I know how to navigate from my 000 to that 1 2 3 4,
Right.
right, or no, sorry, 2 3 4, and whatever that location is, and it can pick it up and put it back wherever it needs to. But you're saying now if that camera's moving, or if the camera's not as precise, then you can actually start to do other things.
Yes.
You're freeing robots from their cage.
Yes.
So, Greg, how do you feel about allowing robots to find and destroy humans?
Yeah, right, exactly. Yeah, no, that's not happening. Yeah, just
That's
my
almost
goodness.
worse than talking about the prequels.
I know. I think it's so funny, because I actually read a headline where they're testing autonomous tanks and M1A2 tanks and stuff like that. So, it's interesting how people use robotics. I think it would be really cool to
Yeah.
use robotic. You know how like automated farming, or rather mechanized farming, like the use of tractors and
Yeah,
combines, it freed human society from picking away at the earth, and it freed us to do things like electrical engineering, right? And then build big metal things and stuff like that. We didn't all have to be, picking away at the ground and growing stuff anymore, unless you wanted to. And that was a big change
right.
in our civilization that happened at the turn
Yeah,
of the century.
definitely. Yeah.
And I think similarly, our technology will enable future factories where there's higher levels of automation, so people don't have to do the drudgery that often happens in these factories. So I think it is transformational. I think we will change the way we make things in a big way.
Yeah,
In the
I think
similar
so.
way
Yeah.
that farms were industrialized, I think the new level of automation that we will see in factories of this century will free us from factories to do more interesting and intellectual things as a society, which could be very good.
Yeah, and I really like I think the way that you talked about indoor GPS. I think that's a very important missing piece. Obviously, at the end of the day, it's using RF and time of flight, like we were talking about
It's a
earlier on the
time of
show.
flight measurement. Yes, we're in all
Right.
cases, all of our technology measures the time of flight. They measure it in different ways. Like the centimeter scale one is an evolution of a technology that's developed 20 years ago, and now it's perfected. And it uses impulses. Okay, it uses time of flight. It uses impulses, and then we could do really cool things. We can like phase code them. We could do all kinds of weird stuff with it. It's actually a very sophisticated technology. Imagine $150 million in 20 years of development. That is what that technology is. And
Yeah.
the millimeter scale one is a lot different. It's just it measures the time of flight, but it does so in a very, very unconventional way. That's actually the stuff we demoed to Jeff Bezos, was the millimeter scale stuff, and that's that's a whole different bird. But it is super unique, and it's kind of incredible. The precision that we get out of it is astounds even us, those of us who've been working on it the past couple of years.
Yeah.
So anyway, we hope to. Well, our plan is to bring the millimeter stuff to market next year. This year, it's the centimeter stuff, the K100, the K300, and now people can buy those products. And next year will be the millimeter stuff. And right now, we're piloting the millimeter stuff with some early adopters and getting feedback, and use the system that we showed at IMTS is the one that the same one that
Yeah.
is with our pilot partners, and they're loving it so far, so good. So
Great.
we'll
Great.
bake in what they, it's kind of the process. You get pilot units out there and see what the market says, and then you tweak it, and that'll be your first release. And we're piloting that one, and we're selling the other one, and we're just cranking away.
It's been interesting how our, you being on the Amp Hour has changed, and you've talked about, we started out having on the show talking about obviously your book and the coffee can radar and all the stuff, and then obviously a lot of ham radio stuff, and just kind of the transition into the startup thing, and it seems like it fits you really well. You're doing some crazy things.
No, thanks,
So
man. Well, it's one of the same. I think your career evolves. I actually believe that there is a career track in startups. Like, you can set yourself up to go from startup to startup over time. You put in your time, you get you get to a point where you've achieved something, and then you may move on, you may do your own thing, or whatever the case. We're all in flux all the time, and
right.
I think it is a viable career path these days. I've realized that when I first started going into startups, I figured I would just do one, and then exit or not, I'm just going to go back to MIT's Lincoln Lab, which I loved it over there. And I'm just going to go back
Yeah.
there. I'm going to do this once, and this is like super risky and all of that. But as it turns out, I don't. I think as an engineering career path, they're not as risky as you might think, because what ends up happening is once you get that first slug of venture capital, and you fill your board with people who have a vested interest in your success, and you deliver, at least maybe you deliver, maybe you under deliver a little bit on some things and over deliver other things, but as long as you're delivering, you're on path, and you're flexible enough, you're pivoting the right way, um, you can generate that next round of funding if you need it, and you can generate revenue. You can, if you just kind of play the game right. I mean, you do right. They say, an old saying from the jazz era. Do right, fly right. If you fly right, you can make a career out of this stuff, and
Yeah.
it's not an unstable thing. Once these companies are funded and they're moving, there's always ways to get funding. There's ways to pivot them into a useful product. They will make it happen, and that's one thing I've learned over the years. No matter how tough the problem is, and anyway, it's doable.
Awesome.
Anyone can do it.
Well, I think I'm excited to hear about what obviously how this works out, but also I assume there's something that's next too, so that's great.
Yeah, there's at Pneumatics we have more stuff. We have we have another thing in the pipeline that hopefully perhaps we can talk about next time on Amp Hour. That
Great.
is that is very cool, and it's actually meant to be lower cost and perhaps target some of these non-industrial applications. We're looking ahead a little bit.
Injectable GPS tags so the robots can find you. That's what I'm gonna just guess that. You don't have to say yes or no. If you say nothing, I assume I'm right.
Rest assured, to all your listeners, that would never work because microwaves cannot penetrate salt water very far, and your body is just made of salt water, so that would never work.
Okay, so tattoos then. It's like outside the skin.
Yeah, right, exactly.
All right, cool. Where can people find more about you and the companies that you've worked on?
I think so we'll list them by latest to the first. So Humatics, if you go to Humatics, Google Humatics Corp, you'll find us. For Hyperfine, Google Hyperfine Research. They are still stealth. You're not going to find much, but Hyperfine's hiring. Humatics is hiring. So if you want to work with me, we're hiring. Send me an email. We're actually looking for a board designer, someone who's really good but has experience churning out circuit boards, like basically like your usual mixed signal digital stuff with a micro and churning it out fast. We want someone with some experience. So if you're that person, send me a note.
Are you an Altium house, I'm guessing?
I believe we don't care as long as you can do it.
Got it.
And then on the other side, there's Hyperfine Research, and they are hiring as well. I believe they're looking for an RF engineer. So if you're an RF engineer looking for something interesting, you can email me. I'll put you in touch with the right people there. And then Butterfly Network is the other one. And they're the ones who are building the first ultrasound on a chip, which they are shipping out pilot units now. I believe they have some large number in the field. I don't know. It's got to be on the order of 1,000, because if you look at their feed, actually, I recommend looking at Butterfly's Twitter feed if you want to see the latest.
Yeah,
it's unbelievable.
Yeah. You want to see a lot of doctors who are like, "What the hell?"
It's pretty cool, man. They're killing it over there, Butterfly, and and I know they're hiring mixed signal ASIC designers. They're looking for one right now. So if you're that person, you can email them or email me, and I'll put you in touch with them. And either way, if you want to join the fun, there's always fun to be had in these companies. So thanks again for listening to us yammer on, because when Chris and I get together, it's kind of fun.
Good times.
It's good times.
Yeah.
Thanks, Chris.
Thanks, Greg. We'll talk to you soon.
Talk to you later. Thank you very much.